right, so I guess we'll get started. My name is Giulia Pintea, and today I will be presenting on a project called Using Quality of Life Scores to Guide Prostate Radiation Therapy Dosing. So, in this presentation, I will be discussing some background on prostate cancer, and then I'll go into the goals of this project, and then I'll go into the method, a little bit of the data preparation process, and the use of transfer learning in our project, and then I'll go into our results with the architecture of our final prediction model, and how that connects with organ sensitivity results that we obtained. So first, a little bit of background. Prostate cancer affects around 200,000 men each year in the US alone, and the treatment options for prostate cancer patients include surgically removing the prostate or prostatectomy, radiation therapy, or a combination of both. And it is a treatable condition if it's caught early enough. However, there are very severe side effects that occur during the radiation therapy and afterwards. So in radiation therapy, the patient lies down like so, and there are beams that deliver radiation to the target area. And however, the beams cannot deliver radiation to the same location the whole time and have to hit the target area from different angles. So the beams move around the target, and the goal is to deliver enough radiation to the target area over the course of 7 weeks. Now, our data is pretty small data set. We have data for about 52 patients. We obtained data on 20 patients at the very beginning of our study, and then 32 additional patients halfway through the study. And these are all post-prostatectomy patients, which means that they all got their prostate removed. And for each patient, we had a computer tomography scan, or a CT scan, and a radiation therapy plan, or an RT plan. And for each patient, we also had results from a quality of life survey, which the patients took before, during, and after the radiation therapy. So here is a picture of a computer tomography scan. It's a cross-sectional image of the body, and in our case, it's a cross-sectional image of the pelvic area. And physicians use CT images to demarcate different organs or different parts of the body, identify cancer in the body, and also to plan the radiation plan and where it's going to be delivered. So as we can see in the image here, we have the bladder, the prostate, and the rectum that are demarcated in different colors, and the hips. And in our data, we have a stack of CT images, which makes, in the end, three-dimensional data for these CT images. As we can see there, we have two CT images as examples, and the areas in yellow represent the bladder, and the areas in orange represent the rectum. And we have the same 3D stack of CT images for the radiation plan. So here we can see the levels at which radiation is delivered, depending on the color on the pelvic area. So the blue indicates the lowest amount of radiation that is planned for the treatment, and the red indicates the highest amount of radiation that is planned for the treatment. Then, as for the quality of life data, we have a patient-reported quality of life scores. Our survey was of 14 questions that asked about different kinds of symptoms. So 7 questions asked about bowel symptoms, and 7 questions asked about urinary symptoms. And each patient chose a score from 1 to 5 to indicate the severity of the symptom, 1 indicating the least amount of symptom severity or no severity at all, and 5 indicating the worst the worst symptom severity. So the goals of our project were to basically develop deep learning approaches to correlate these CT scan features and the radiation plans with changes in quality of life data from the prostate cancer patients, and hopefully find a relationship between the radiation dosage to different regions of the bladder and rectum in particular, and see how those correlate with quality of life changes. So first, we had to classify our patients between those who had a significant change in symptoms and those who did not. So we looked at the bladder and rectum independently, and for each organ in our prediction model, we intended to have CT scans and radiation plans for either the bladder or the rectum as the input, and then we wanted the output to be a binary class that would predict whether or not that patient had a change in symptoms over the course of treatment. So the output would be a binary class that would be 0 or 1, 0 indicating no changes in symptoms, and 1 indicating a change in symptoms. And to make this binary classifier, we divided the 14 survey questions between 7 urinary questions and 7 bowel-related questions. And then for a given symptom, we selected the highest score that was selected throughout the treatment. And then we located the baseline score, which was the score selected for the given symptom before the beginning of the treatment. And then we subtracted the baseline score from the highest score and then summed it all up for symptoms related to that specific organ. And the value that resulted from this formula could range between 0 and 12. So we arbitrarily selected a cutoff value of 6, so that patients that had a value that was greater than or equal to 6 would be classified as those who did have a change in symptoms, and those who had a value that was less than 6 would be classified as those who did not have a change in symptoms. So in order to visualize this, we have a plot here. So on the x-axis, we have the sum of changes for urinary symptoms in this case. And on the y-axis, we have the first 20 patients that we worked with sorted by patient ID. And we can see that the cutoff value is at around 6, so that those patients that have data points that are in the blue area are those that did show a significant change in symptoms, and those in the red area did not. Then, because we only had 20 radiation plans and 20 CT scans for our beginning of our study, which is very small, we had to employ a data augmentation method. So we used image flipping on our 20 CT scans and radiation plans, and we flipped them both vertically and horizontally to produce 60 new images, and for a total of 80 that we could work with. And here we have an example with the original CT image cropped around the bladder with the contour of the bladder on top of it, and the corresponding horizontal flip. Now I'll go into our use of transfer learning in this project. So at the very beginning, when we were making our first attempts in making a convolutional neural network to see if it would be able to predict a binary classifier based on the CT images and the radiation plans, we were getting very bad results. We got an accuracy between 40 to 60% for urinary and rectal symptoms, and there were two main issues that we ran into. We had data leakage. So basically, for the training set, we had all of the flipped images, and for the testing set, we had only the original non-flipped or not modified images. And there was a really strong relationship between the flipped data and the original data, since it's the same image, just it's flipped in another direction. We had to cut that connection, but that extremely lowered the accuracy. And then another problem that we faced was overfitting, because as we let our model train for longer periods of time and for more steps, the model overfitted the training set. And we knew we needed more data, but we couldn't find ways to get more. So we decided to use transfer learning to find the near optimal starting points that we could use for our prediction model. So we use the autoencoder. The autoencoder is an unsupervised learning method where there is no need for labeled data, and the goal of the autoencoder is to reconstruct the input that we feed it. So in this example, we would have X in the input layer, and then as the autoencoder runs, it deconstructs X and reconstructs it to basically give a reconstructed version of the input. So we get X prime as the output. Now, in our project, we wanted to input our CT scans and our radiation plans into the autoencoder so that it would reconstruct them, and as it trains over a higher amount of data, it can provide us with with nearly optimal starting points or weights that we can then use for our prediction model. Now, to do this, however, we needed, of course, a lot more data for the autoencoder to train. So we used curvature-based interpolation in order to obtain about 1,520 new CT images and radiation plans. So in this method, we will basically take a stack of CT images for one given patient A and another patient B, and then interpolate each of the slices of these two stacks to create a new stack for fake patient C. And we did this because if we were to do this with our original prediction model, we wouldn't have a way to know if the fake patient is one that has a significant change in symptoms or not, and we would have had to find a way to interpolate the quality of life scores as well. So if it is very hard to label interpolated data in our context, and if we were to randomly label them, the algorithm wouldn't have learned anything. While if we did develop a method for it, then our model would just be learning the method that we used. Now here is an example of the interpolated images. So we have two original images cropped around the bladder for patient A and B, and then patient C is the fake interpolated patient with the CT image that results from interpolating patient A and B. Now I'll go into our final prediction model and more into the architecture of our model. So as I mentioned earlier, we use the autoencoder, and what basically happened in the autoencoder is that we entered the CT images and radiation plans, and then it went through 3 convolutional layers to deconstruct the images, and then it went through 3 deconvolutional layers to reconstruct them. And there was also batch normalizations and max pooling that were part of the architecture, which I'll go into in a minute, since we use those also for the prediction model. And then once the autoencoder was done running, we were able to obtain these near optimal starting points from all the interpolated data. And also, at this point in time, we received the data on 32 additional patients. So we now have a total of 52 non-interpolated, non-modified patient data. So for our prediction model, we used the same convolutional neural network architecture as our initial attempts, except this time we used the optimal starting points that the autoencoder was able to give us. So in our prediction model, it's 3-dimensional convolutional neural network with 3 convolution layers with 3 by 3 by 3 filters. And the pooling method that we used was max pooling. So every time the model would go through the convolutions, the max pooling method would keep the strongest value for each pixel, and it reduced the feature size from 48 by 48 to 1 by 1 pixel. And then for our activation function, we use the exponential linear unit, or ELU function. And we also used batch normalization in all of our layers, since it allowed for equal updating of the weights, and it allowed our model to converge at a faster rate. Then we also used a dropout layer at a rate of 40% because we still wanted to avoid overfitting as much as possible, since 52 patients is still a very small data set. And for our loss function, in order to keep track of the loss during training, we used a cross-entropy function that was minimized through backpropagation. And then during our training process, we had our 52 original patients that were randomly assigned to either a training set or a testing set, such that we had 39 patients in the training set and 13 patients in the testing set. And our model had a learning rate of about 0.001, and we also used 5-fold cross-validation on the training set. And in order to quantify error, we used the mean square error. So as we can see here in this graph, for when we enter the rectum related data in our model, the loss is decreasing as the model is training, and it's indeed converging. And we can see the same pattern for the data for the bladder. Now, I'll go into the process of 5-fold cross-validation. So with the 39 patients that are part of the training set, that set is divided into another training set of 31 patients and a validation set of 8 patients. So we can see the training here is marked in green and the validation is in orange. So basically, each of these folds initializes a classifier, so we can select a model that performs the best. So basically, as the model keeps training, it trains on the data that's marked in green and tests on the orange. And then in the next fold, there is another group that's selected for the validation set, and it trains on that group of green training patients and then tests on a validation to improve what it's learning and how it's learning. And then in the end, it tests on the original 13 patients that were assigned in the testing set. So overall, just to visualize the architecture of the prediction model, the CT scans and radiation plans go through the 3 convolutional layers with all the characteristics that I just described to you. And then and the output layer, it produces a confusion matrix, which gives us an idea of how many patients were guessed correctly based on the category that they were assigned to. And we also, of course, obtain the accuracy. So as for our results for the bladder data, we obtained a 50% accuracy, which is as good as flipping a coin, which to us indicated that there is hardly a relationship between the CT image scan features and the radiation plans and the quality of life data. And there might be more factors out there that could explain why there are changes in quality of life. And then for the rectal symptoms, we got an accuracy that ranged between 61.5% to 84.6%, which was pretty good. And we obtained such a wide range because we ran it multiple times by changing the training and testing sets. And we noticed, because we got such a wide range, that our model is sensitive to which patients are included in which set. But we do believe that having much more data would be able to stabilize this accuracy to one number. And now here I have an accuracy table for the rectal symptoms. So based on this table, we have the 13 patients that our model tested on at the very end after training. So out of the 10 patients that did not have a change in symptoms, our model was actually able to predict 9 out of 10. And out of the 3 that did have a change in symptoms, our model was able to predict 2 out of 3, which overall seemed pretty good to us. But after this, we wanted to see how these results connect to organ sensitivity and see if there are any regions of the bladder and rectum that are particularly more sensitive to radiation. So we explored this relationship between spatial radiation dosage and quality of life scores by using analysis of variance, or ANOVA. So to do this, we split the bladder in top and bottom and the rectum between front and back. And we looked at this distribution of radiation in both regions and how that changed based on whether or not patients manifested a change in symptoms. So for the rectal symptoms, we found that those who experienced significant changes in the following 5 symptoms, diarrhea, urgency, tenderness or pain, abdominal cramping, and passing mucus, had a significantly higher radiation dosage in the front and back of the rectum. So for each analysis, we got a plot as shown here. Now, on the x-axis, we have the category based on the 0-1 category based on whether or not a patient experienced changes in rectal symptoms. So we have the 0-1 category. And then on the y-axis, we have the distribution of absolute radiation dosage in milligray. And this is specifically looking at the pain symptom, which is listed as number 3. For the rectum. And we can see that when we look at the radiation distribution for category 1, it is much higher than compared to category 0. So those who did have a significant change in symptoms, so those in category 1 did have a significantly higher radiation dosage in the front of the rectum, which is just for this plot. However, for the bladder, we didn't have as many significant results. We only found that those who experienced changes in the urinary symptom of urgency had a significantly higher radiation dosage at the top of the bladder. And we think that we didn't have as many significant results because it is very much consistent with what we found in the deep learning. Because if there is basically no relationship between the radiation dosage and quality of life, then that would explain why we didn't get as many significant results. However, now our team wanted to ask, how high does radiation have to be before symptoms start manifesting? So in order to do this, we wanted to use logistic regression because we believe that finding safe dosage thresholds would help doctors prescribe better radiation dosages and prevent this decline in quality of life that seems to be occurring during treatment. So in a logistic regression model, we have the total absolute dosage in milligray as the independent variable, and the dependent variable is the change in a given symptom, which is 0 or 1, as it has been throughout our project. And in order to find these dosage thresholds, we wanted to identify where we had 0 false positives and 0 false negatives, such that, for example, there were no patients that were mistakenly classified as being in another category. So in order to visualize this, we will use a logistic plot. So on the x-axis, we have the absolute dosage in milligray. And then on the y-axis, we have the probability ranging from 0 to 1 of having a change in a given symptom. So this is a plot specifically for rectum symptoms. And the dashed line in the middle of the plot indicates the threshold that we had to move in order had to change in order to see where we had 0 false positives and 0 false negatives. So in this case, on the plot, we can see that also with the accuracy table that there are 0 patients that have no change in symptoms that are falsely put into the change category. So basically, there are no mistakes in category assignment. And then we move the threshold again and find where there are no patients that are in the change category that are mistakenly predicted as having no change in symptoms. And by using these 2 thresholds, we can obtain this boundary that we deemed as a safe dosage threshold based on our data. So for the front and back of the rectum, we got interesting results. For the front of the rectum, we had a dosage threshold between 2100 milligray and 4300 milligray. And for the back of the rectum, we found a range between 400 milligray and 1700 milligray. And here is a visual to see how these 2 ranges differ. So we can see that the back of the rectum needs significantly less distinctly less radiation dosage, while the front of the rectum can handle a higher amount. However, for the bladder, we got very different results. For the bladder, we had from 0 to 4600 milligray for the top, and for the bottom, we had from 3200 milligray to 5400 milligray. And here we can see that these 2 ranges overlap by a lot, and we can also see that the logistic curves do not look like logistic curves, they look like linear curves. So this further showed us that the relationship between the radiation dosage and changes in quality of life scores when it comes to the bladder in particular is very ambiguous, and there have to be factors outside of this that could further explain why there are patients that do show symptoms with different amounts of radiation. So overall, we did find connections between spatial radiation dosage and changes in quality of life symptoms only in the top of the bladder and both the front and back of the rectum. And the results that we found were consistent across methods. And then we were also able to, in fact, get these dosage thresholds that we can deem as safe before symptoms start developing. However, further research should try to extend deep learning to all quality of life scores from 1 to 5 instead of having just a binary classifier, and hopefully be able to classify based on individual symptoms as opposed to an entire category of urinary symptoms or an entire category of bowel symptoms. Any questions? Oh, yes.
So I know you looked at bowel symptoms and urinary symptoms. Did you do any logistic models that use combination? Like, do you know patients who
That's a really good question. We actually did not look at combinations of symptoms, but it's definitely something interesting that we'd like to look into, since we only grouped urinary symptoms together and only bowel symptoms together. But that's definitely something worth looking into. Yeah. Yes.
I know you mentioned at some points that the autoencoder, I'm sorry, I'm going to say, but the autoencoder is actually really confusing. You have to play around with it a lot. Would you say that for future projects you would use an autoencoder, or do you think it's not reliable enough to do for this, a project like this?
I think an autoencoder would be very useful for small data sets when there is no way of getting a larger data set, or when data interpolation is very ambiguous, as it is hard to label interpolated data. However, of course, we had to fidget a lot with the autoencoder and change the functions that we were using, since although we saw that the autoencoder worked for other studies, our context was different, and we definitely had to fiddle around with it just because of the context. But I think it would be a very good method to use only for like pilot studies, or just any study that involves small data sets. I think it would be worth using.
So when you determine these safe dosing ranges, was there any medical recommendation beforehand? And how do they compare? So,
Doctors don't know. When we did a site visit, because we were working for the UNC Edinburgh Comprehensive Cancer Center, and we asked doctors what would be helpful before we were done with the project, and they said they don't know how much is too much. And that's why they asked us to look into this. But we did find a few studies that tried to explore this as well, and we got similar results as them too. So. Any other questions?
Just like a background question for patients who have been through prostatectomy. Is it required for them to have radiation therapy afterwards, or it's only because you mentioned your examples around like 52 patients who already got their prostate removed and then they got their radiation after, but just from like a medical perspective, I know like patients usually have the option to do radiation before, or if that doesn't work out. Like it's just like so I would just ask like is it like what's the relationship between like you have to have the radiation therapy after, or just the recommended?
From what I know, at least from my conversations with our sponsors from UNC, they said that usually the prostatectomy is not enough to get rid of the cancer, so it's usually just it's usually a combined treatment. So prostatectomy occurs, and then they go through radiation therapy just to get rid of all the cancer that is there. But usually there are also patients that don't go through prostatectomy and just rely on radiation therapy all throughout, unless it's a very severe case. But that's I don't have a lot of biomedical background myself, so that's the extent of the knowledge I have on this. Mm-hmm. Okay. All right, thank you so much.